Hey guys, Mrs. Levenseller here, and today we're going to talk about compound inequalities. So you just learned all about singular inequalities, where we are just going to have one inequality sign. And right now we're going to talk about compound inequalities. So your learning target is I can solve and graph compound inequalities. And the first question is, what is a compound inequality? Okay. Well, compound, right, if we're thinking science or if we're thinking math, compound is just multiple things put together, right? Something that's made up of more than one piece. So a compound inequality is just two or more inequalities to describe a solution set. So that means we're going to have two types of inequalities, and we are either going to have numbers that fall within both of those. We're going to have numbers that fall within both of those restrictions, and it might be places where those restrictions, or sometimes we call them constraints, those inequalities. Sometimes we have solutions where they overlap, and sometimes we have solutions where they're separate. So if you think about a Venn diagram, there's that, and there's that. Okay, so there are two types of compound inequalities that we're going to talk about. The first one is an intersection of the two inequalities. So that would be just like here. Oops, I didn't mean to do that. Just like in here, the intersection where those two pieces are overlapping. So that creates an and type inequality, or an intersection, where we're going to say we want a number greater than this, and that same number also has to be less than something else. Okay, so it's sandwiched between two values. The union, or the or type inequality, is going to be when we can have an inequality that falls in either camp. So it could be either less than a certain number, or it could be greater than a certain number. It doesn't have to be both at the same time. So that gives us, all of these, either over there or over there. Those would be your or type inequalities, compound inequalities. Okay, so think about the word, when you see the word and, or when you see like a sandwiched inequality, that is the intersection, so that's where those inequalities are overlapping. Whereas when we see the word or, we can have either or, all right? So let's talk about a couple examples here. So again, and, when we see the word and, we're looking for the overlapping areas. And it's easiest when we see that on a number line, okay? So let's look at this first example. So example 1, I'll use the other color. We have x plus 5 is greater than 10, and x minus 2 is less than 11, okay? So our job is to find solutions that satisfy both inequalities at the same time. So first, we have to solve, right? So if x plus 5 is greater than 10, I'm going to take away 5 from both sides. So x is really greater than 5. I'm going to still bring down that word and, because it's an important part of my solution, is to know whether it's an and or an or. And then I'm going to solve the second inequality by itself. So we get x is less than 13. All right. So what this is really saying is that we need values that are greater than 5 and less than 13 at the same time. So I'm going to put that on my number line. So I have 5 and 13. And remember, just like we talked about last time, if there's no equal to in the inequality symbol, we can circle the number, but we're not going to fill it in because we're not including 5 or 13 as part of our solution. And then watch what happens here. So I'm going to use two different colors. So the first, I'm going to graph x is greater than 5. Okay. So I'm going to circle 5, and everything that's greater than 5 would be everything to the right, okay, towards 13. Then if I want x is less than 13, I'm going to shade everything to the left of 13, right? I would want all the numbers that are smaller than 13. So what we're looking for is numbers that are both greater than 5 and less than 13 at the same time. That word "and" is important. Well, numbers like 6, 7, 8, 12, those numbers are both greater than 5 and less than 13 at the same time. So my actual solution is everything between those two inequalities, those two numbers, okay? So that's why we call it an intersection. It's where those two inequalities intersect. A few ways that we can write this: we can use our interval notation like we looked at last time. So we have everything from 5 up to 13. If I'm not including 5, I'm going to use a soft bracket. I'm not including 13, I'm going to use a soft bracket as well. So that's one way to represent my solution set. Or we can write it as a set. So I'm going to use a set brace here. And we're talking about x as our variable. So all the numbers x such that, and then what I really want to do is I could write these two inequalities. So I could say x is greater than 5 and x is less than 13. But sometimes that's a little bit long for us to write. So actually with intersections, with ands, we can combine them into one statement by putting x in the middle and saying, okay, x is less than 13, and then flipping this second inequality. So instead of us saying x is greater than 5, really saying 5 is less than x, all right? And so that is what I would put on the other side of the x value there. So this is the best way to represent that, or interval notation, depending on what they're asking for. This is certainly okay, but it's not the cleanest, all right? So that's one possibility for an and inequalities when we actually see the word and, all right? Let's check out another example. And this time, we don't see the word and. We see 5 is less than or equal to k minus 2, all right? And it's also saying k minus 2 is less than or equal to 11, all right? So what we really have here are two inequalities, but they've been stuck together. They've been sandwiched together. So my first step is to pull them apart into their two separate inequalities. So we would say 5 is less than or equal to k minus 2. Because it's all sandwiched together, I know it's an and. So and k minus 2 is less than or equal to 11. All right. When it's an and inequality, your two inequality symbols should always be facing the same direction. So that's a little hint there. So when we solve this, 5 is less than or equal to k minus 2. Well, all I have to do is add 2 to both sides. So 7 is less than or equal to k, or that also tells us k is greater than or equal to 7. And if I add 2 to both sides over here, so same process to solve, k is less than or equal to 13. All right. So here we are looking for numbers that are greater than or equal to 7 and less than or equal to 13. So again, I could represent this on a number line, 7, 13. This is actually very similar to the one we just solved. So I'm going to circle 7. Because it has the equal to here, I can fill that in. I'm including 7 as part of my solution. And I want all the numbers greater than 7, which would be everything to the right. And then 13, circle that value. Again, I'm filling it in because of the equal to here, and I want everything less than 13. Where those two inequalities overlap, their intersection is right in the middle there. That is my solution, okay? Because numbers like 8 and 11, those are both greater than 7 and less than 13 at the same time. As an interval, we could say we're going from 7 to 13 with hard brackets this time because I'm including the numbers. Or if I put it in my step builder notation, we would have, so I'm really just going to combine this and this, right? So 7 is less than or equal to k, which is less than or equal to 13. So there you have it, 3 ways to represent the same solution, okay? And depending on what your directions ask for is which one you want to do, but for the most part, I just need you to be able to read all of these different types, okay? And so let's look at one more. This time we're going to talk about an OR. And usually when you graph an OR type inequality, your graph is going to go in opposite directions. Not always. If an OR is overlapping, we actually end up with an all real numbers situation. So like if I had my number line with numbers going to the left and to the right, and it was an OR, not an AND, that's a situation where we would have all real numbers as our solution, because every single number, whether it's less than this or greater than this, would be part of my solution. But let's look at the example here and see what we can come up with. So the first problem says 3d plus 3 is less than or equal to -1, or 5d plus 2 greater than or equal to 12. All right. ORs are never going to be connected like the one that we just looked at here. They're never going to look like that. They're always going to have the word OR in between them. So when we solve, we want to solve each one separately because they're two separate problems. So take 3 away from both sides here. 3d is less than or equal to -4. Divide by 3. d is less than or equal to -4/3. Or, here I have to take away 2. 5d is greater than or equal to 10. Or d is greater than or equal to 2. Okay? So let's graph that on a number line and see what that looks like. So we have 0 in the middle here. -4/3 is -1 1/3. So it's about here. And then 2 would be about there. All right. So I'm going to circle -4/3. Because of the equal to, I'm also going to fill that in. And then we have all the values less than or equal to -4/3. So that would be everything in this direction. For 2, d is greater than or equal to 2. So again, circling it, I can fill it in because we have the equal to. And then we want everything greater than or equal to 2 would be everything to the right. All right. So that's one way to represent our solution. If we wanted to use set notation, all we would have to do is put the values here and enclose that in our set braces, which actually, did I use the right one? Sorry. When I did set notation down here, I should have used k to match that variable, not x. Sorry. Just reminded me of that. So that's why I use d here to match my variable. And then if we want to do interval notation, so remember your number line goes from -infinity up to +infinity, right? So we would start our first interval to show that we're using all of this stuff would be from -infinity up to -4/3. We never include -infinity, but -4/3 is colored in, so we are going to include that. My second interval would be from 2, because we're starting with 2 and we're including 2, so I'm going to use a hard bracket, all the way up to +infinity. We never include infinity. And when you have more than one interval, you want to connect them with what we call a union symbol. So it just really looks like a big capital U in between. That tells me that I have this or this, okay? So really that capital U represents the word or there. All right, and I think that's about it for compound